Okay, now we're going to solve exponential equations. Let's solve this equation. The left-hand side is an exponential expression. The right-hand side is just a number. We see that 8 can be written as 2 cubes, so that's equivalent to this equation, and we see immediately that the solution is 3. We know already from the graphical approach there's only one solution. Okay, now let's solve 2 to the x equals 7. Well, x is just simply log base 2 of 7, which we can approximate on a calculator by using the change of base formula. Let me write that down. If we wanted to use a calculator, we could do log of 7 over log of 2. By log, I mean the log button on your calculator. So that's log base 10. You could also use a natural log. Okay, the next is to solve this equation. This is a little bit more complicated, but not that much more. We know still that 8 is equal to 2 cubed. So 3 is equal to 5x minus 1. And solving this equation gives us that x is equal to 4 over 5. Now we're solving this equation. That's tricky because we need a calculator to approximate, but we can get an exact answer this way. Let's still write 5 as 2 to some power, but it's exactly 2 to the log base 2 of 5. That's exactly what log base 2 of 5 is. It's the exponent 2 needs to give you 5. So when we do that, we see that 3x must be equal to log base 2 of 5. So we can then add 1, divide by 3 to get the answer x is equal to 1 plus log base 2 of 5 over 3. We can approximate this on a calculator again using the change of base formula to evaluate this, and then we'll add 1 and divide by 3. Okay, now let's solve this. By the way, in the above, I've left this as the exact solution. As soon as you use your calculator, it's no longer exact. We only approximate. So we have another example with 2 different bases, and we have exponents, both of which depend on x. So what I'm going to do here is rewrite the left-hand side as 10 log base 10 of 7 to the x. That is 7 to the x. And I'll do the same for the right-hand side. So basically, I'm changing the base of the exponent this way. Doing that, I can equate my exponents, just like I've done here. I want to remark here that you can actually go directly from the first step to this step if you think of applying log base 10 to both sides. It's perfectly fine to think that way. So the exponents come down in front using the property of logs. Number 3. Then I distribute the log base 10 of 3 into the x and the minus 2. I subtract this from both sides and factor out the common x. My goal is to get x by itself on one side. I see that this is linear. You should think of these as some numbers that you're writing down in some weird way, but they're just numbers. And then you divide both sides by that expression multiplying x. And we can write that expression actually as log base 10 of 7 over 3 using the second property of the logarithm. It's a little mixture of algebra and properties of logarithms. This is something you can approximate on your calculator directly because you have this log button on your calculator, which is log base 10. Okay, the next thing I want to talk about is the application on compound interest. I'll start off with an example, and then we'll try to think about it more generally. But let's say you invest $1,000 in a bank, and it's earning interest at a rate of 2% per year, compounded annually. That means after the first year, you have the original amount you invested plus 2% of the amount you invested. This is called the interest. So if I factor out 1,000, I get this expression for that. I don't want to multiply that out to get a number at this point, because I will be aiming to find a pattern. And the second year, your investment basically is the end result of the first year, which is this. It's the same as that. Plus, you're going to earn interest on that very sum, so you're going to add 2% of that. So you factor out this common factor, and what you get is 1 plus 0.02. If you simplify that, you see the 1 plus 0.02 is then just squared. So you have this amount of money in your account after the second year, or upon completion of the second year. Upon completion of the third year, you can see what happens. It's analogous to the second year computation, except now you have a square here. So you get this as an answer. You can work through those details. And similarly, after t years, you have this expression. So the exponent there is the time you invest. I want to point out briefly here, I've written it in the notes, that this a of t does not mean multiplication. This is just a way to write or the amount after t years. Just think of this together in one grouping. In general, you may invest a different amount. We'll call that P. That's the principal. That's the amount you invest. R is the annual interest rate, and T is the amount of time you have invested measured in years. Years is related to this annual rate. So since it's an annual rate, we're going to measure in years. If we compounded n times a year, what that means is that after t years, we've compounded nt times, so we will replace t with the number of times we compounded, which is nt. But each time we compound, which could be a number of times a year, we will only use a fraction of the rate. So we will replace the rate in this equation here with r over n. So we get the more general formula that the amount you have in your account after time t years is the amount you invested times 1 plus the rate over the number of times per year you compound to the number of times you compound power. Okay, I'd like to do an example. Here's a question. How long does it take to have $1,600 if you invest $800 at a rate of 3% compounding quarterly, n equals 4? So let's identify things. This is r if we convert it to a decimal. We're compounding quarterly, which means n equals 4. We're compounding 4 times a year. We are investing $800. And we want to know when we have this amount in our account. So what we're interested in is finding the t in years. So we have this equation. We want to solve it for t. So the first thing to do is to isolate the exponential part. The plan is to eventually have a logarithm in front of this expression in order to pull that variable out of the exponent. So we'll see how that plays out in this example. Take some experience to know where you're going with this. So we divide both sides by 800. We get a 2 on the left-hand side. And this is now what we have on the right-hand side. We change the base of the exponent. If you would like to think of that as applying logarithm to both sides, that's fine. So I'm going to just do that here. If you want, you can think of writing both sides as 10 to the log of 2, 10 to the log of the right-hand side, and then equate the exponents. Okay? What's the advantage of doing this is that now this 4t becomes a factor instead of an exponent. And now we can divide by what's multiplying t on both sides of the equation. We get t equals log of 2 divided by 4 log of 1 plus 0.03 over 4. We can approximate this with our calculator, get an idea that we need 23 years of investment to get $1,600 from there. That's providing, of course, the interest rate doesn't change, and so this is a single investment that you agree to hold in an account at this particular interest rate, let's say a CD. This is generally how you would solve for t. Okay. By the way, in general, for a problem like this, what you want to do is identify each of the numbers given to you in the problem as part of your equation, as part of your A, P, R, N, or T, and then solve for whatever you're looking for. It may not be T. I'm solving for T here because that's where the logarithms come in. If T is given to you and N is given to you, then this is no longer an exponential equation. It becomes an equation you may need roots for. Your variable is not in the exponent. Then you will not need logarithms to solve it. Okay, here is a theoretical note. The right-hand side of the formula looks like this. I'm just going to rewrite this a bit. So I can rewrite the exponent here as n over r times rt. Why am I doing that? Because this is the reciprocal of that. And now I use the property of exponents to write it in this way. But this expression in the brackets is approximately e for n large. What is e? It's about 2.71828. You can put it on your calculator. See, when n is large, the r over n is small, and this is 1 over that, so that's big. So for instance, you can try to evaluate this when this is 1,000 and this is 1 over 1,000. And see what you get. You're going to get something very close to this number. So for large n, so if you're compounding very frequently, you can use this simplified formula. A equals P e to the RT. So now T is time in years, R is the annual rate, and P is the amount invested. So notice that there's no n in this equation. And the reason is because it's replaced with basically this e situation. This is compounded continuously, so infinitely often. Okay, so for instance, the amount in the account, if you compound continuously, is a of t, and that is the amount invested. E to the rate t is the time in years. Let's do an example. How long must you invest $1,000 to have $1,500 with a rate of 2% annually? That's the interest rate, and you want to compound continuously. So let's identify these values. 2% is 0.02. 1,000 is how much you invested. 1,500 is how much you want, and you're interested in knowing the time. So we are solving for t. How do we do that? We divide both sides by 1,000. We get this expression. Now we, if you like, change the base to e to match the right-hand side. So now we're going to, if you like, you can think of 1,500 over 1,000 as e to the natural log of 1,500 over 1,000. And then you equate the exponents. And that gives you this expression here. Alternatively, or you can think of applying the logarithm to both sides, and note that natural log of e to the 0.0t is the same as 0.02t. Then divide both sides by 0.02 and you have your answer. This is exact. You put that in your calculator and you will get the approximation.